This is the second video on shapes of molecules and ions, where I'm going to go through examples to show you how to determine the shapes of molecules when both bonding pairs and lone pairs of electrons are present. So first example, if we look at ammonia, NH3, so nitrogen is in group 5 and it's bonded to 3 hydrogen atoms. In total, we've got 4 pairs of electrons. 3 of them are bonding pairs, and there's 1 lone pair. So it's a tetrahedral distribution of electrons around the nitrogen. So the difference with this is that the lone pair on the nitrogen repels the bonding pairs more than the bonding pairs are repelling each other, and so the bond angle is slightly reduced compared to the usual tetrahedral shape, so that's 107 degrees instead of 109 in a standard tetrahedral molecule. And then the shape of the NH3 is called pyramidal. There are a few things to take note of when we're dealing with molecules that have both bonding pairs and lone pairs present. Firstly, you never quote a bond angle that is between a lone pair and a bonding pair. So all the bond angles that you come across, they're always going to be referring to the angle between 2 bonding pairs of electrons. The second thing is that lone pair repulsion is greater than lone pair bonding pair repulsion, which in turn is greater than bonding pair repulsion. And it's important to keep that in mind in all of these examples. The second example, if we look at water, H2O, oxygen is in group 6 and it's bonded to 2 hydrogen atoms. There's 4 pairs of electrons present, 2 of them are bonding pairs and 2 are lone pairs. And again, we'd expect a tetrahedral distribution of electrons around the oxygen. And because the 2 lone pairs are repelling each other more than they're repelling the bonding pairs, the shape of the water molecule is V-shaped and the bond angle is reduced to 105 degrees. In general, 1 lone pair of electrons reduces the tetrahedral bond angle by about 2 degrees, and because water has 2 lone pairs present, the bond angle is reduced by 4 degrees. Next example, if we look at an ion, PCl6-. So phosphorus is in group 5, so it would normally have 5 outer electrons, but the negative charge on the ion means that we add 1 more electron onto phosphorus's outer electrons, giving a total of 6 outer electrons. If we draw out the dot and cross diagrams, we can see that there's 6 pairs of electrons. All of them are bonding pairs, which means that they repel each other equally, and the shape of this ion is octahedral. Last example, ClF4-. Again, the negative charge means we add 1 electron to chlorine's outer electrons. Chlorine is normally in group 7, so adding an extra electron means it now has 8 outer electrons. So drawing out the dot and cross diagram again, we have 6 pairs of electrons, and so there's an octahedral distribution of electrons. So there's 4 bonding pairs and 2 lone pairs. And if you remember from my first video on shapes of molecules and ions, electrons like to position themselves so that there's lowest repulsion between them. And because the lone pairs repel each other more than they repel the bonding pairs, they would be positioned 180 degrees apart, with the fluorines perpendicular to the position of the lone pairs. And the shape of the ion is called square planar.